So in this video, we're going to look at bases, and we're going to look at strong bases. And strong bases are things that undergo 100% ionization or 100% dissociation in water. There are 6 common bases that you need to know, and I'll just go ahead and show you the figure from the textbook here. So this is table 17.7, and if you look at these, you can see there's basically 2 different kinds of bases. There are group 1 hydroxides, so these are group 1A hydroxides. So with the exception of hydrogen at the top, you've got lithium, sodium, potassium. You would also have things like rubidium hydroxide and cesium hydroxide, except they are extremely unusual. I'm not even sure if you can buy them, but if you can, I'm guessing you're paying thousands of dollars a gram. And we're looking at the next group, group 2A, and so strontium, calcium, and barium are also considered strong bases. And in general, the 2A hydroxides are. Now, one of the problems with the 2A hydroxides is some of them are not very soluble. So, for instance, what about magnesium hydroxide? Is magnesium hydroxide strong or weak? And the answer is, yeah, could be. So, it's slightly soluble in water, which means you can't really make a very strong solution in water. And so, it's really kind of silly to talk about it being a strong base if you can't get it to dissolve in the first place. Just like an acid, a strong base is something that completely dissociates. And so here's a nice figure here from our textbook. So you can see when sodium hydroxide dissolves in water, it completely breaks down and makes sodium ions and hydroxide ions 100% of the time. Now, from what we saw in the acid chapter, we can also calculate pH of these strong bases quite easily. For example, what is the pH of 0.1 molar potassium hydroxide in room temperature water? So we can go ahead and write down the equation because it is a strong base. It completely dissociates. We can see that if we had 0.1 moles in a liter of potassium hydroxide and it undergoes 100% dissociation, then we will have 0.1 moles per liter of hydroxide ion. And we can do this a number of different ways. The easiest way is to calculate the pOH. The pOH is the negative log of the hydroxide concentration. So that is the negative log of 0.1. And again, just like before, the number of significant figures becomes the number of decimal places when we log it. So 2 significant figures becomes 2 decimal places. So that is 1.00. And that's the pOH. And remember, the pH and the pOH add to 14 at room temperature. And so we can get the pH by subtracting 14 minus pOH. And we can do this in our head. This is just 13.00. And again, at room temperature, anytime the pH is above 7, you've got yourself a basic solution. One interesting thing that we didn't really have to worry about with acids is that some of these bases produce 2 hydroxide ions. So for example, if we wanted to know the pH of 0.1 molar strontium hydroxide, so strontium hydroxide is a group 2 soluble hydroxide, we would have to remember that when it dissolves in water, it is forming 1 strontium, which we don't care about, but it is forming 2 hydroxide ions. So that's what we got to pay attention to. So if this is 0.1 mole per liter, this will be 0.1 mole per liter because we're undergoing 100% dissociation, but this is twice 0.1 moles per liter, which of course is 0.2 moles per liter. So we can do the same thing. We can calculate the pOH, negative log of OH minus, but now because the strontium hydroxide gave us twice as many hydroxides as before, we now have a concentration that is 0.2 molar, and if we take the negative log of that, we get 0.70. Again, remembering that the number of significant figures here translates into the number of decimal places here. Of course, that's not the answer. The answer is the pH. And we remember that the pH and the pOH add to 14, so we have to subtract the pOH away from 14 to get the pH. And again, we can do this in our head. This is 13.30. So compare. So our 0.1 molar potassium hydroxide had a pH of 13, but our 0.1 molar strontium hydroxide has a pH of 13.3, so it is more basic, right? It's 0.3 unit more basic than the potassium hydroxide is. So the strontium hydroxide, if you like, is a more intense base than potassium hydroxide.